Today we'll talk about embedded surfaces and the curvature tensor. We're actually jumping over a few topics, so if you're watching this a few weeks from today, I will have probably backfilled those topics. But I'm very eager to talk about this topic, mostly because my students have been very eager to hear about it. I've been promising them that their understanding of curvature is just 10 minutes away, and I stand by it. So the topics that we've missed are not relevant for what we're going to talk about today. However, before I move on with the subject of embedded surfaces and the curvature tensor, I will go back and fill those topics. But right now, I want to give you the very minimum of information to understand the concept of curvature. It's a very important topic, and it'll take several lectures to cover, or maybe to only scratch the surface, but you have to start somewhere. And I think a good place to start is to give you the very minimum of concepts that introduce the concept of the curvature tensor and mean curvature, my favorite symbol. So, in order to follow this lecture, I would recommend that you review two lectures from the past. One on the fundamental objects in Euclidean space, and two, the lecture on Christoffel symbols, and maybe look at the covariant derivative again as well. Because the next few minutes will step by step follow that pattern. And we'll realize that that pattern will actually break, and we'll have to introduce a new idea, because embedded surfaces are not like Euclidean spaces, because they're curved. So we will see that one of the ideas of Euclidean spaces will not apply to curved surfaces, and that will be precisely the moment when the curvature tensor arises. So let's assume now that you've reviewed those lectures just now and follow the same procedure for introducing the covariant basis, the metric tensor, the contravariant metric tensor, the Christoffel symbols, the covariant derivatives, and see, well, we'll have to take a slightly different approach. So let's consider an embedded surface. I'm not particularly good at drawing surfaces, but let me try. Let this be a two-dimensional surface embedded in the three-dimensional Euclidean space. That's important. Just as before, we're going to refer the surface to a coordinate system. The space that surrounds it, called the ambient space, is also referred to a coordinate system, but for today it's actually not important. I'll just mention that the coordinates in the ambient space will still be denoted by zi, but I do not believe that zi today will make an appearance. The surface itself will be, because it's two-dimensional, will require two coordinates in order to be mapped. And those coordinates will be called S1 and S2. So just as before, we use the letter Z for just about everything and let the indicial signature determine what quantity we're talking about. Now that letter will be S. So the surface is denoted by the letter S, and the two coordinates on the surface are S1 and S2. So you may imagine coordinate lines may look something like this. These are the lines of constant S1, and this could be the lines of constant S2. Okay. Collectively, these coordinates will be referred to as S alpha, and we'll use Greek letters as opposed to Latin letters to refer to indices that have values 1 and 2. Latin letters have values 1, 2, and 3. So that's the distinction. So now S alpha. And once again, we'll introduce the position vector. So by introducing the position vector, we're actually taking advantage of the Euclidean nature of the ambient space. The position vector exists in the ambient space. There's one position vector that points to every point in the ambient space. So it's an invariant field with respect to an arbitrary origin. It's an invariant field with vector values. We're going to look at the restriction of that vector field to the surface. So we will only consider the position vectors that end up on the surface. So take a moment to visualize that. It's an invariant field defined on the surface. The restriction of the position vector to the surface. Restriction just means we're not going to look at the values of the position vector outside of the surface. Only on the surface. Once again, this is possible because the ambient field is Euclidean. Great. Now what we realize is that this invariant field can now be referred to coordinates. So it can be considered a function of coordinates. So now the position vector r, a moment ago it was just an invariant field of an invariant space. Now it's an invariant field that is a function of the two coordinates, s1 and s2. And according to our convention, we suppress the indices of function arguments. And in fact, we will write this as r of s, which means r of s1 and r of s2. So if we consider the surface of a sphere, s1 and s2 are commonly taken to be theta and phi. On a torus, it's another set of two natural variables. On an arbitrary surface, it's an arbitrarily chosen map. Okay, so following the pattern that we started in the Euclidean space, we can define the covariant basis. It is defined by differentiating the position vector with respect to each of the variables. All right, let's try and draw what that might look like. I actually have yellow chalk here, which is very convenient. So previously I said that these are lines of constant S1. So these would be lines of constant S2. So these are lines along which S1 is changing. So dr ds1 is likely pointing along this line. It's tangent to the surface. So it might look like something like this. This might be S1. And similarly, S2 might look something like this. S2. Okay. In the book you can find the drawings for the sphere, ellipse, I think, and maybe a couple other common surfaces. And of course, their length very much depends on just exactly how the surface parameterized with S1 and S2. And what else is important to realize? It's important to realize that these vectors are tangential to these curves as viewed in 3 dimensions. So these two vectors are tangential to the surface. I'm just appealing to your geometric intuition at this point. So these two vectors combined determine the tangential plane to the surface. So it is often said that these two vectors are the tangential plane. They're the two tangential vectors, or they span the tangent plane. And it's also important to realize that they don't really lie within the surface, because it may not have been possible for a straight vector to lie within a surface unless it's flat or plane, or maybe a developable surface. We'll talk about that at another time. But generally, they're tangential to the surface and don't lie in the surface. That's obviously important. Why don't they lie in the surface? Even though it's even impossible because it's curved, but, well, it's because the surface is curved. So curvature is beginning to rear its beautiful head. Okay, so that's the tangent space. And also, I will not draw it, but I will write it. There's a well-defined, almost a well-defined unit normal. Why am I saying almost well-defined? It's because there are two of them, one pointing in this direction and one pointing in the other direction. So let's just choose one of them. It's actually not important at this point that it obeys some kind of right-hand rule. Let's just arbitrarily choose one of the two normals and define it by, denote it by the letter n. And of course, it's a vector quantity. Now, n is a unit vector that's orthogonal to both S1 and S2. We might as well write this property of S1 and S2 and the property of the normal. It's orthogonal to each one. So here's your pair of identities that express it in the algebraic language. And it's also unit length, which can be written this way. So this is more of a characteristic of the normal rather than the tangential vectors. Equals 1. So that's the unit normal. Of course, it's very interesting to express the components of the normal explicitly. They would have to be expressed because this vector does not lie in the tangential plane. It may not be expressed with respect to S1 and S2 because it's not in that plane. It's actually the most not in that plane it can be. It's orthogonal to that plane. But we can still express and decompose that with respect to the covariant basis in the ambient space that is borne by this coordinate system. So that's a task for a later date. There is a beautiful expression and it's obviously very useful. But all we need to know about the normal today is that it's orthogonal to the covariant basis and its unit length. Okay, moving on. Once we have the covariant basis, we can form the covariant metric tensor by the same pattern as before. It is denoted by S alpha beta, and is defined as the pairwise dot product of the covariant basis elements. So there you go, great. Now we have the metric tensor just as before. Once we have the metric tensor, we can do all sorts of things on the surfaces. Once again, we'll save that for a later date, but measure lengths, measure lengths of curves, measure lengths of areas of patches, and so forth. So just to look at a concrete example, on the sphere of radius r, refer to the standard angles theta and phi, where theta is this angle that determines the inclination with respect to the axis. I guess that's the longitude angle. And phi determines the meridian. Then for that coordinate system, the covariant metric tensor has the following form. R squared, 0, 0, R squared, sine squared theta. That's for a sphere of radius 1. Excuse me, that's for a sphere of radius r. Okay. So once we have the covariant basis, we also have the contravariant basis that is defined as the matrix inverse of the covariant basis. S beta gamma equals the Kronecker delta of alpha gamma, where the definition of that object is obvious. Okay, so now, well, of course, the contravariant basis. S alpha equals S beta with the index raised. Okay, now we have almost our full collection of the metrics. Of course, there's also the determinant of this object, whose square root is called the volume element, maybe more appropriately the area element. There are Levi-Civita symbols, which will come later, but their definition is very similar, except they have 2 indices, not 3. And of course, there is the Christoffel symbol, which is very important for the definition of the covariant derivative. So let's derive the Christoffel symbol. Where can I write it? So I'm about to write something I will erase, so it won't occupy a prominent position. But let's define it by analogy with the Euclidean space, where it was defined the following way. If we consider, let's see, the derivative of the consider the derivative of the covariant basis with respect to one of the coordinates. So we'll have ds alpha, ds beta, ds alpha, ds beta. So these are 4 vectors. Each one of these 4 vectors can be decomposed with respect to the basis itself. And let's call those coefficients the elements of the entries of the Christoffel symbol. Gamma, alpha, beta, as gamma. And that's the definition of the Christoffel symbol. So the analogy with Euclidean spaces seems to be complete. Except, of course, there's one problem with it. And the problem stems from curvature. This derivative, the rate of change of the covariant basis element, if you just imagine what happens to S1, let's look at ds1, ds1. So it's the rate of change of the first basis vector with respect to the first coordinate. Right? As you can see, it'll curve with the surface. And when it curves with the surface, its rate of change will not lie in the tangential place. It will have a component normal to the surface. I think it's quite apparent. It'll point slightly in that direction, because that's the direction in which this vector is changing. It's picking up more and more of that direction. It curves. So this derivative lies in the overall ambient space. It does not lie in the tangent plane. And it is therefore not possible to decompose it with respect to the covariant basis, which is only capable of expressing vectors that lie in the tangential plane. So this definition is not possible, and the cause of this state of affairs is curvature. So this actually is a very positive step. It gives us a handle on the concept of curvature. So I'm about to erase the board and show you how to fix this problem, which is done in there are two ways of doing it. They're completely equivalent, and both of them will lead to the concept of curvature. I'll show you one and show you the other. Okay, in one moment. But for now, let me box this and cross it out so that this is captured on video. Okay, we're back, and you will recall an expression similar to this one in Euclidean spaces. I'm not sure if I've ever written on the board, but it's certainly very prominent in the book. We don't emphasize it early on. We show it as one of the interesting consequences of the primary definition that we use, the one that doesn't work on surfaces. But a definition such as this of the Christoffel symbol is actually very important. It shows its intrinsic nature. It shows that if we know the metric tensor and how the metric tensor changes from one point to another, which is captured by these partial derivatives, then we actually have the Christoffel symbol. That means that the Christoffel symbol can actually be defined strictly in terms of the covariant derivatives, the derivatives of the covariant metric tensor. That's actually very important. It's one of the ways to save the situation in our case right now. So our definition that we attempted here through the vectors didn't work, but we have the metric tensor, and we therefore have this definition. And remember what we want the Christoffel symbols for. We need the Christoffel symbols primarily in order to define the covariant derivative. And for the covariant derivative to have the tensor property, in other words, to produce the tensor output for tensor inputs, we only need a symbol, such as the Christoffel symbol, that changes according to a certain rule under a change of coordinates. And a symbol defined in this way will change according to the right way, in order to the way that would lead to a great covariant derivative. So on the surface, by analogy, or actually in any space, or in any manifold, in which the metric tensor is defined the way we did it, or arbitrarily given a priori, if you write down a definition like this, you will have an object that changes according to the way you want from one coordinate system to the other. And it is therefore can be used in the definition of the covariant derivative, and everything's great. So this is one of the ways, the intrinsic way of introducing the Christoffel symbol, and it works just fine. However, we don't want to quite give up on our extrinsic approach that uses the covariant basis, because it's a very geometrically intuitive and very visual object. We don't want to give up our geometric intuition just yet, and we really want to be able to use and work with the covariant basis, because it's such a great object. So I will now write down what previously was used as a consequence of the definition of the Christoffel symbol, but it will now serve as the definition of the Christoffel symbol. And it is this. Alpha beta is this dot product. But remember before, it followed from this definition by dotting both sides with the contravariant basis element. And these were the explicit components of this object with respect to this object. Now it can no longer be interpreted as the explicit components of this object with respect to the contravariant basis, because this object cannot be decomposed with respect to the covariant basis. However, it's still 8 numbers, and because it has this form, the same form as in the Euclidean space, of course it'll change by not necessarily the same rule, but completely analogous rule to the way it changed in Euclidean spaces. Because this can be taken as the definition in both cases, and then all of the analysis would be the same, and the rule by which this symbol is changing, actually that was one of the topics that I'm planning on backfilling. Today is April 21st, so if you're watching this a month or so from now, it's probably backfilled already, and you've seen it. If you're watching it shortly after I uploaded this, then you might not have seen it, but of course it's all over the book. Okay. So this changes according to the rule that we want, and we can therefore use this object to define the covariant derivative, which is defined by the exact same rule as before. It's the partial derivative plus a Christoffel adjustment term for each of the indices of the object. All right, so now let's assume that the Christoffel symbol has been defined and that the covariant derivative has been defined. And that's now because it's defined by the same rule. And let's now study the properties of the covariant derivative. So it's a big jump, but it's fair because it's exactly analogous. So you can review those lectures and replace z's with s's and in Latin indices with Greek indices, and everything will work the same. Except one thing, and that's the one thing we'll concentrate on right now. Let's talk about the metronyllic property as applied to the covariant basis. Okay. So here's the big question. What is the covariant derivative on the surface, the covariant surface derivative of the covariant basis? In the Euclidean space, in the ambient space, this was 9 zeros. That was the metronyllic, one of the elements of the metronyllic property of the covariant derivative. The covariant derivative applied to the covariant basis and the contravariant basis is 0. Or a whole lot of zeros. In this case, it would have been 9 zeros. But here we have 4 vectors. And we should have some doubt as to whether or not this would be 0, because after all, these guys do curve. And because this is designed to capture the rate of change of this vector, because they do curve, maybe we won't quite get 0. Okay. I realize now I should have left a little bit more space here. You'll see in a moment why. So let's write down this definition. So we have d, by definition, it's ds beta, ds alpha, minus, because it's a covariant type thing, minus gamma alpha beta omega, I will use here, s omega. Okay, is this 0? Well, we're not sure. Previously, we concluded that in the Euclidean space, that this expression was 0 was a very easy conclusion, because this term was exactly this term, because this term was merely the decomposition of this term with respect to the covariant basis. So at this point, we're observed that this expression is easily seen to be 0, and that was that. Now we have this definition of the Christoffel symbol. We've had to give up, it's not up to us even, that this object can no longer be decomposed with respect to this basis. So none of these 4 vectors can be decomposed with respect to the covariant basis. So we can no longer conclude that this is 0. In fact, it's not. But let's see what we could conclude. Let's dot both sides of this expression. I'll use yellow chalk so you see the contrast with a member of the contravariant basis. So I want to dot both sides of this expression by S gamma. Dot this. Dot this. And dot this. S gamma. All right. Now we have 0. Can you see that? That this expression is 0? Why? Because this right here is delta gamma omega. So contracted with the Christoffel symbol, it'll replace omega with gamma. So this is gamma alpha beta. And this is gamma alpha beta by this very definition. Now it seems to be that alpha and beta are switched, but of course this is symmetric with respect to alpha and beta. It's a very important exercise to prove that this object, even though it doesn't appear from being written in this way, that it's symmetric with respect to alpha and beta. But it is actually true, and very important for you to see why. So you would notice that ds1, ds2 equals ds2, ds1. We've certainly observed that and talked about it before. So even though alpha and beta switched, we see that this is still gamma alpha beta. It's gamma alpha beta minus gamma alpha beta. So now we do have 0. 0. So what's the conclusion? The conclusion, if we look at this, is to realize that what this identity is saying, this being 0, is that each one of these 4 vectors is orthogonal to the tangent plane. In shorthand, it's orthogonal to the surface. So each one of these 4 vectors, since it's orthogonal to the basis elements, and the contravariant basis elements define the same plane, they lie in the same plane, and of course span the same plane and all of those things. Very easy to show because they're linear combinations of the covariant basis elements. Easy to show. So each one of these 4 vectors is orthogonal to the surface. I'm pausing for drama. So being orthogonal to the surface, each one of these 4 vectors must be proportional to the normal vector with 4 coefficients of proportionality. Because it's 4 different vectors, right? There's no reason why they should be unit vectors or any known length vectors. They're 4 different length vectors. 2 of those vectors are the same because of symmetry, but otherwise there are some vectors that happen to be orthogonal to the surface and therefore proportional to the normal. So those coefficients of proportionality are denoted by B alpha beta. So here is, let's write down this observation, that the covariant derivative of the covariant basis, each of those 4 vectors is proportional to the normal with some coefficient of proportionality, alpha beta. Of course, we can get an explicit expression for this by dotting both sides with the normal. So if you want this expression explicitly, here it is, alpha beta equals the normal dotted with this covariant derivative. And from this way of writing, it is apparent that this object right here is a tensor. Tensor, tensor, invariant, so the whole combination is a tensor with respect to changes in surface coordinates. So this object right here is a tensor. It's very important, therefore it's meaningful. And it's also symmetric in alpha and beta. Well, that's a step ahead. I'm a step ahead of myself. So this is called the curvature tensor. That's how the curvature tensor arises. It arises in a very natural way. This expression right here fails to be zero because of curvature, because the surface curves. That's intuitively clear. We figure out it's proportional to the normal. So let's give some notation to those coefficients of proportionality. We learn that it's a tensor, and it is therefore called the curvature tensor. So, a very exciting moment. One of my favorite symbols appearing for the first time on the board. Oops. Right here. Okay. So, let me just wrap this up by defining mean curvature, a very important invariant. So remember, one thing that I didn't mention that we have just because we have the covariant metric tensor is the ability to juggle indices. So the index juggling convention is available automatically as soon as there is the metric tensor. So these indices can be raised or lowered with the covariant and contravariant metric tensors. So we can certainly consider B alpha beta with the first index raised, and we don't have to pay particular attention to which index is first and which index is second. That's only because this symbol is symmetric in alpha and beta. Otherwise, I would have taken great care to pay attention to the order of alpha and beta. And of course, we can now contract on these indices. And because we're in the tensor framework, what we get for free is the invariant property of the result. So B alpha alpha, probably my favorite object, is known as mean curvature. I usually don't write too many words on the board, but this one needs to be written. And of course, it can be from this definition. If you need an explicit definition, well, just the fact that it's a contraction of this and is an explicit definition, but it might be useful to also write this formula, where you have to be a little bit careful. I raised the index under the covariant derivative sign. So I raised the index beta on both sides and then contracted it, which is only a valid operation if this symbol, if this derivative is metronilic with respect to the metric tensor. And we notice that it is not metronilic with respect to the covariant basis. So there may be some doubt as to whether or not it's actually metronilic with respect to the covariant basis. Well, it turns out that it is. And it can actually be seen from here, because it is easy to show that this definition is equivalent to this definition, and this definition leads to the metronilic property, that we actually do have the metronilic property with respect to the metric tensor for this derivative operator. So this is valid, and so now you have the definition of mean curvature. And I just want to say it also follows from contraction of this object, which is defined over here. And there you go. We now have the concept of curvature, as I promised, and it was a very easy thing to introduce because now we have all elements of the tensor framework. Thank you very much.